All right, welcome everybody to our first video lecture. So if you haven't done so already, go ahead and get out those guided notes that I have for you for Chapter 4, whether you're doing this on the computer, on your technology, on a tablet, or if you've printed them out or you're just taking notes by hand. We are going to be following along with these, so make sure you have those out and ready to go. So in Chapter 4, we're looking at uses of the derivative. So the primary topic of discussion here is the concept of maximum and minimum values, because maximizing and minimizing is a very huge application of calculus that we have. So to start off, we're just going to define some of these terms here. So suppose P is a point in the domain of F. We say that F has a local minimum at P if f of P is less than or equal to the values of f for points near P. So f of P is less than or equal to the values of f for points near P. So this is the key idea right here. The function value at P is smaller than everything else around it. That's what we mean when we say local minimum. So it's maybe not necessarily the smallest value of the whole function, but in its immediate vicinity. For everything around it, it is the smallest. So we then similarly say that f has a local maximum value at P if f of P is greater than or equal to the values of f for points near P. So if it's the largest thing in its immediate vicinity, right, bigger than anything else around it, we call it a local maxima. Okay? The general term for these that we use is local extrema. So if you hear that term being used, it just means local maxes and mins, all combined. So let's go ahead and look at an example. So consider the function. We have x cubed minus 9x squared minus 48x plus 52. Let's go ahead and take a look at this function on Desmos. So here we have x cubed minus minus 9x squared minus 48x plus 52. Now notice, if we close this out here, this is not very helpful, right? Just looking at Desmos here, we can see that the function has a couple different segments to it, but we don't really know what's happening outside of these values. Now, the nice thing about Desmos, we could zoom out if we wanted to, take a better look at it here, but you can see this function grows very steeply and is quite thin. So viewing on a standard Desmos window is not the most effective way of working with this function. We can actually much more easily work with this function dealing with derivatives. So now, let's figure out where this function is increasing and decreasing. So first thing we need is the derivative. So we're going to get f prime of x. So to get this, we need to use the power rule, right? So the power rule, we get derivative of x cubed, that's 3x to the 3 minus 1, so 3x squared. And then minus 9 times 2x to the first, right? So that's minus 18x. And then minus 48 times 1, right? Because the derivative of x is just 1. So minus 48. And the derivative of 52 by itself as a constant is just 0. Okay. So when we're looking for where the function is increasing and decreasing, remember increasing and decreasing are talking about where the derivative is positive or negative. So to find where it's positive and negative, instead of trying to just plug in every possible point, let's find the points where the derivative f prime of x equals 0. So if we find the points where it's 0, then that means all the points other than these should have either a positive or a negative value. So scroll down a bit here. We're going to find where the derivative is 0. So we have 3x squared minus 18x minus 48 equals 0. Notice a common factor of 3 in all of these. I'm going to go ahead and just divide the whole thing by 3. That's going to leave me with x squared minus 6x minus 16 equals 0. Okay. So now this is factorable. So we go ahead and factor this. So this is x minus 8, x plus 2 equals 0, which gives us, of course, the two factors 8 and negative 2. So these are the values where the derivative is equal to 0. So what we're going to do is we are going to draw a number line. I'm going to thicken this up a little bit. And on this number line, I'm going to go ahead and put these values. Okay, they don't really need to be evenly spaced or anything, just putting them on here. So I'll put negative 2 here, 8 here. And I want to find out what happens between these values. I want to find out what's happening at all of the other points besides these, because I know that the derivative is 0 at these 2 points. So everything outside of those must be either positive or negative, and that's what I'm looking for. So we need to find if f prime is positive or negative on these intervals. So what we're going to do is we're just going to pick a sample point. Okay, so we can pick any point we want from this interval, and then any point we want from this interval, and then any point we want from this interval. Okay, it doesn't matter what point it is, they would all give us either a positive or negative answer as long as it's a part of the same interval. So generally the rule of thumb is we want to pick the one that's easiest for us. So for this one, for example, I'm going to go ahead and get f prime of negative 3. The interval in the middle, anytime 0 is an option, usually 0 is a good choice. And then for this upper one, let's do f prime of 10. It doesn't make too much of a difference. Now, if I find these values, f prime of negative 3, so if you plug that into the derivative, so again, plugging it into this one up here, so into this one, we get f prime of negative 3 is 33, and that's positive, clearly. F prime of 0, plug it into the derivative, that's just negative 48, which is less than 0. And f prime of 10 gives us 72, which is positive. Okay. So we got out a positive, a negative, and a positive. So that means that since the derivative is positive, the function is increasing. When it's negative, the function is decreasing. And then positive again means the function goes back to increasing again. So now we have a nice look at the behavior of this graph, right? We see that it goes from increasing to decreasing to increasing, right? Something like that. And we know from the Desmos graph that this is in fact the case. So all we need to do now is to get a couple of ordered pairs. So let's actually find the coordinates of these points. So if we go back up and look at the original function, so this one up here, Look at that function. And then we find f of -2 and f of 8. Well, f of -2, it turns out, I'll save you all the work right here, that's 104. And f of 8 is -396. So you can see fairly quickly why Desmos wasn't working out too nicely for us, because this function, like we saw, is just huge. So we see from this behavior that this point down here at -2 is bigger than everything else in its immediate vicinity, which means that this one is a local maximum. So we have a local max at the point -2, 104. And then this one here at 8, everything else around it is bigger than it is. So that makes it a local min at the point 8, -396. Okay, so this would be our solution if we were looking for local maxes and mins. Okay. Now if we look on Desmos, if I zoom this out a bit, Desmos actually can tell us what the max and mins are. And you see the max is -2, 104, and the min way down here is 8, -396. Okay, so that's our function. Get used to this function. We're going to be working with it for a while here. But that's our local max and our local minimum value. Now, for any function f at a point P in the domain of f, where f prime of P equals 0, or f prime of P does not exist, or it's undefined, the point P is called a critical point, also abbreviated CP. Now, a critical point, this is a point where the derivative is either equal to 0 or does not exist. Critical point indicates that a function might, an emphasis on the word might, have a local max or min there. Right? We saw in the last example the derivative where that was equal to 0, that gave us our maxes and mins. These critical points tell us this is probably a good spot for a max or a min, but it's not a guarantee. So just because we have a critical point doesn't mean that we automatically have a max or a min. We actually have to test it. And we have two tests to be able to do this. So first up, we have the first derivative test. Okay. So the first derivative test says, suppose P is a critical point of a continuous function f, right? So we have a critical point, a point where the derivative is 0 or does not exist. Moving from left to right, if f prime, the derivative, changes from negative to positive at P, then f has a local minimum at P. And if f prime changes from positive to negative at P, then f has a local maximum at P. Okay, so let's see what this looks like here. Oops. So here we have an example of a minimum. So local min would be right here. So that's our point P. Notice everything to the left on this side over here. This function is decreasing, right? So we have f is decreasing, right? Or in other words, f prime of x is negative on this side. And over here on the right-hand side, we have f is increasing. All right, so f prime of x is greater than 0, which means our point P here is a local min. Okay, and that's where f prime of P equals 0. And again, if you look at that tangent line, it's horizontal there. And because we switched from decreasing to increasing, it gave us a local minimum. Now, if we look at the other case, we have a graph that looks like this. This point now, this is still our point P, but this time we have f is decreasing, right? So f prime is less than 0, or excuse me, I apologize. This is f is increasing over on this side. So f prime is greater than 0. There we go. All right, the function's going up. It's increasing. But then when we pass P on this side, f is decreasing. Right, so f prime is less than 0 over here. So the function's going down. So if we have a function that's going from increasing to decreasing at the point P, right, where we have a slope of 0 up here, that means that this point P must be a local max. So this is our first derivative test for local maxes and mins. Okay, so we look at the derivative around the point, around the critical point, and determine if it's going up to down or down to up. Okay, there are possibilities where it could go up to up or down to down, but those would not be maxes or mins. Now we get to the second derivative test for local maxes and mins. So here we're looking at the concavity. We're looking at the second derivative. So suppose that P is a critical point of a continuous function f, and f prime of P equals 0. If f double prime of P is greater than 0, so in other words, if the second derivative is positive, or if the graph is concave up, then f has a local minimum at P. And if f double prime of P is less than 0, so the graph is concave down, then f has a local maximum at P. Now, the second derivative test, it has one kind of setback, which is that if f double prime of P, if the second derivative equals 0, then this test is what we call inconclusive. Just another word for not helpful. So inconclusive meaning that it doesn't give us any relevant information. So this one, it's a little counterintuitive, right? Because you think concave up, you would think maybe maximum, concave down, you would think minimum, but it's actually the opposite. The reason for that is because the concave up graph looks like this, right? Like a U, right? That's concave up. And the critical point occurs where the derivative is 0. And so that is down here at the bottom. That's where our slope is horizontal. So this one is actually going to be a local min. Whereas when the graph is concave down, now the critical point, that 0 slope, is up here at the top. And so that one is going to be a max. Okay, so it's a little counterintuitive, but drawing out the graph of the concavity can be a real helpful way of looking at it. Okay, so again, if we have f double prime of P is positive, it's a min. And if we have f double prime of p is negative, that gives us a maximum. So let's look again at the function we were working with earlier. So use the second derivative test to confirm that this function has a local maximum at -2 and a local minimum at 8. So we already found these, but now let's use the second derivative test to just verify it. So earlier when we were working with this one, so we found f prime already, right? F prime of x, that was 3x squared minus 18x minus 48. So to get the second derivative, we need to just take the derivative of this one. So again, we're going to employ the power rule here. So power rule says we have 3x squared, bring down the 2, so that becomes 6x to the first, minus 18 times 1, and then minus 0, right? That's the 48. So now we also know that f prime of -2 and f prime of 8 are both 0. Okay, and that's going to be important to use our second derivative test. So now, all we need to do for our test here is just find the value of the second derivative at these critical points. So at -2 and at 8. Okay, so at -2, we get 6 times -2 minus 18. That's -12 minus 18 is -30, which of course is less than 0. And 6 times 8 minus 18, that's 48 minus 18 is positive 30. Which it really doesn't matter what the number is. All that matters is whether it's positive or negative. Okay, so for this one, because we know that -2 is a critical point, and we know that the graph is concave down there, so picture that concave down graph, right? That tells us the point is going to be a local max. So it's local max at x equals -2. And then this one, right, this is concave up because the second derivative is positive. So that means we have a local min at x equals 8. So next up, we're going to go ahead and try another example just from scratch, and we're going to try to find critical points, classify them as maxes, mins, or neither, because it's possible a critical point could be neither, and we're going to use both tests to verify the result. Now, ordinarily, you wouldn't need to use both tests in the same example, but because I want to show us extra practice with both of them, we will do both. You'll see that they do give us the same thing. So, to start us off, we need to first get the derivative. Because to get a critical point, you need to take the derivative, set it equal to 0, and solve. Okay, and you'll hear that come up a lot, right? Take the derivative, set it equal to 0, and solve. So for our derivative here, we have g prime of x. That's going to be, so this requires use of the product rule. So first times derivative of the second plus second times derivative of the first. And what does that leave us with? Well, on this first one, because of the chain rule, we get e to the -3x. The derivative, again, is e to the -3x, but then times the derivative of -3x, right? So that would be times -3. So this is -3x e to the -3x. And then plus, e to the negative 3x times the derivative of x, which is just 1. So this is just e to the negative 3x. Okay. So now, let me go ahead and factor. Okay, so notice there's a common factor of e to the negative 3x here, so let me just pull that out. And we're left with negative 3x plus 1. And then to find the critical points, we're going to set this equal to 0. Okay, so when we set this equal to 0, we get two cases. We get e to the negative 3x equals 0, or negative 3x plus 1 equals 0. Now, for this one, e to the negative 3x equals 0. We need to find what value of x makes this happen. Well, think about any positive value of x you want, and you just get e to the negative 3 times whatever that number is. But negative powers just become fractions, so that doesn't make it 0. So we plug in a negative number. But any negative number makes the power positive, which just keeps making e get bigger. That's not 0 either. So we say, okay, well then, how about I plug in 0? Well, when you plug in 0, you get e to the 0. However, e to the 0 is 1. Anything to the 0 power is 1. So in this particular case, there are actually no values of x that will make this function equal 0. And if you look at the exponential graph, exponential functions have an asymptote, a horizontal asymptote at 0. They never actually hit 0. So this one is going to provide us with no solutions. So we're not really going to worry about it. And then this one over here, this one's going to give us x equals 1/3 if you solve for it. So this right here, this is our critical point. So we only have one, but this is our critical point. Now, once we have the critical point, we can go ahead and start running tests to determine whether it's a max or a min or neither. So first up, let's go ahead and do the first derivative test. Okay, so we're going to create our number line, put our critical points on it. Our only one is at 1/3. So put that on there. And now we're going to just pick a point to the left, pick a point to the right. Doesn't matter what they are. And then we're going to see whether the graph is increasing or decreasing. So anything to the left of 1/3, so as I just mentioned, I'm going to pick 0, because anytime you can, it's usually a good idea. So g prime of 0, that's going to be e to the 0 times 0 plus 1. Okay, 0 plus 1. So that's just e to the 0, which is 1, which is positive. Okay. So we have an increasing function here. And then something bigger than 1/3, just pick 1, right? So you could pick anything you wanted, but 1 seems to be the easiest choice. So g prime of 1, that's going to be e to the negative 3 times 1 times negative 3 times 1 plus 1. So that's e to the negative 3 times negative 2. E to the negative 3 will always be positive, because again, the negative power just makes it a reciprocal, a fraction. Doesn't make it negative. The negative 2, however, so this is what's making this one negative. So this is less than 0. So the function is decreasing after 1/3. So what that tells us is that this point at 1/3, since we're going from increasing to decreasing, this must be a local max. Okay. And that would be our first derivative test. So now for the second derivative test, well, first we need to actually get the second derivative. So let's get g double prime of x. Okay, so g prime, you can use any form of g prime that you want. If you want, you can go all the way back up to this one over here. You're going to have to do a product rule on this. But I'm just going to go ahead and use this one, because I'm going to use the product rule anyways, so at least I'm only taking one derivative this way. So let me take the derivative here. So this is going to be, so first times derivative of the second plus second times derivative of the first, which we saw that one earlier. Notice each of these has a common factor, right? E to the negative 3x times negative 3, e to the negative 3x times negative 3. I'm going to pull that out of all of it. So that's negative 3 e to the negative 3x. What's left here is just a factor of 1. And then over here we have negative 3x plus 1. So we're going to get negative 3x plus 2. And that's going to be g double prime. Okay, so that's our second derivative. So now to test our critical point, we're just going to get g double prime of 1/3. And again, it doesn't even really matter what the number is. All that matters is whether this number is positive or negative. So this is going to give us negative 3e to the negative 3 times 1/3 times negative 3 times 1/3 plus 2 so that is negative 3 e to the negative 1 times negative 1 plus 2. So that's just negative 3 over e, right? If I just turn e to the negative 1 into 1 over e, which is a negative value. So since the second derivative is negative, that tells us the graph is concave down. And since the graph is concave down, so again, that means that it looks like this. So that's our point with our zero slope, which means it must be a local max. So we have a local max at x equals 1/3. Which is exactly the same result that we got by using the first derivative test. Again, you would not need to use both in any given example, but this is just so you can see that they do both in fact give us the same thing. Okay, so that's the end of section 4.1. That's our introduction into the concept of maxima and minima values and how to compute them. So we'll be back for section 4.2, and that's all I have for this one.